It is now afternoon, yes.
Now can I add my blue little upload?
Yeah, go ahead. Hello? 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 A little bit of latency in my end. All right, I'm going to give people a chance to get logged in, and then we'll start. Go ahead and turn this on. Figure out what Tristan's going to be doing for the next hour. That's going to make your tongue blue. So another nerd shirt today, the elements of humor, sarcasm. All right, so I think everybody who's going to watch is in. Well, they should be. The plan for today was I wanted to go ahead and take a look at the worksheets and just pick out a few problems to work on. Thank you. I get a lot of my nerd shirts from Think Geek is where I typically go for nerd stuff. That and Amazon. All right. So just about set up here. Everybody, hopefully you guys all finished the worksheets, right? Does anybody have any questions about anything before we start, or did you want to work on a particular problem? This is your guys' time. I'm thinking of this being more of like a review day than anything. You should have by now have gone through all the lecture content and started into, well on your way into the worksheets, getting ready for that quiz this week. And I called it. I said that the lawn guy is going to come right when I start lecture. He almost always does on Thursday. And there he is. So sorry, there might be a weed whacker going here for the next few minutes.
I'm sorry if I'm smacking in the video.
Yeah, can you? What are you going to be doing? Are you going to play the game? What are you going to do for the next hour? What are you going to do for the next hour? Let me know, please. Come here. Come here. What are you going to do for the next hour? Stick your tongue out. I told you, hey, your tongue blew. All right. So let me go ahead and just pull up Canvas. Let's go ahead and get started. He'll figure it out. He's going to be playing a Pokemon game probably while I'm teaching. There's a Pokemon fighting game on the Switch that he likes to play, a Pokken tournament.
And I keep beating everybody's butts.
Do you?
Uh-huh.
That means you need to start playing online. All right, I think for the first few of these, we don't have to do really any drawing. So I'm just going to do it on the... Let me move my face over here. There. All right, so I did want to take a look at the first two here. These aren't actually these were actually old test questions, and on some of them I forgot to remove the point values. But yeah, you need to do all of the questions. Don't worry about the points; ignore them. I don't even use those. This is from like back when I did have it as a test question. All right, so the question here is basically gives you a reaction. I'm hoping just immediately looking at this, you guys should be able to see what mechanism that is. So what do you think? What is that number one? What mechanism did that undergo? How do you know it's SN1? So, anybody, how do you know that it's SN1? Yep, it's tertiary. It's a tertiary substrate. You want to just go ahead and take a look. Here, we have 3 carbons coming off this carbon, so that is SN1. So the next thing, so in order to answer this question correctly, you need to be able to figure out what the rate law is. So it's saying here that you are going to double the concentration of both the substrate and the nucleophile, and this should only the substrate should have an impact here. So this should be B is the correct answer, double the rate. Yep, double the rate. So suppose in a hypothetical scenario, suppose this question was asking about, say, an SN2 mechanism. So suppose changing both the concentration of the substrate and the nucleophile, how would that affect SN2? What do you guys think? What would be the correct answer then for SN2? These choices. Yep, D would be the correct answer then if this were the case, or if it was an SN2. Because if you double the rate of both, you're going to increase it by a factor of 4 times. Where only one of them is involved, you just double the rate. All right. Next one here is which of the following reagents is least effective in generating sodium ethoxide? And you're given the structure. So it works out where all of these are potential acid-base reactions. When it's saying least effective, it's basically which one of these is the weakest base out of all these. And I believe that C is the correct answer here. Weakest base is hydroxide. Yeah, typically the way that we generate this particular compound, sodium ethoxide, is typically by taking ethanol, which is drinking alcohol, and treating it with sodium metal. And that actually deprotonates it right away. So, much better way. All right, I want to go ahead and do this one here, number 3. If you guys, if we were going to lab this summer, this is actually one of the experiments that I actually cut out. So I cut out some experiments to make it so we only had 1 lab per week, where a normal semester in summer we have 2 labs per week, except for on exam weeks. Anyway, this was one of the reactions we were going to do, the SN1 reaction. Very straightforward stuff in the lab. But let's go ahead and take a look at it on paper. All right. So I'm going to go ahead and draw this flat because it's not a chiral center anyway. So you don't have to really worry about the chirality here. All right. So in that particular problem, they're telling you that it's HCl and H2O. Something I wanted to show you down here, a little side note. If you have H2O and HCl, these actually react together. So recall back when we were going over the leveling effect of water with acids. This has a pKa of -3. This is a super strong acid. So this is actually going to react with water. So, we used, I think it was pink arrows last time. Let's do orange arrows today. So, that showed it very well. Like that. And then we generate the hydronium ion. Like that. So sometimes you may see, over the arrow, you may see something like HCl, H2O. You might also see something like H3O+. These are equivalent, writing it this way or this way. All right, so I'm going to go ahead and actually, over here, I actually want to draw out the hydronium ion because I want to show the mechanism here. You need to actually draw this out if you're going to do the mechanism. So we're going to use one of the lone pairs on oxygen to grab the H. Like that. And then you can go ahead and show the leaving group leave. And then we get a carbocation intermediate, like so. And then you still have the chloride ion from earlier. And I'm going to draw some lone pairs in. The one that's actually doing the attack, though, I want to go ahead and draw orange. It doesn't matter which one, just one of the lone pairs. Just putting emphasis on that it's a lone pair doing it. And then we get our final answer. Like that. So the cool part about this lab here is basically you have all this in water in the lab, and it works out where these are all aqueous, but this compound is not water soluble. So what ends up happening, you just mix them in a funnel, and it's an enclosed funnel, and you keep shaking it, and then eventually a second layer starts to develop on the top, and that's this compound. And then we just we purify it by removing the water, and then collecting it, and then analyzing it a little bit, and yeah, it works very, very easily. Very quick lab. All right, are there any questions about this one? Any questions? Okay. All right, so one of the questions, or one of the things in this question here, let me show you right here. So it's saying to about molecular geometry. What that's basically getting at is that I want to make sure that you're drawing your intermediate carbocations as a planar molecule. You're drawing it flat. So don't put a dash and wedge on a carbocation center. They're flat. All right. This one here is asking you to fill in the arrows. I have an idea. I think I'm just going to screen cap this. I got an idea how we're going to do this. So I can screen cap it. I should have thought this out beforehand about drawing on the page here. I don't usually do this kind of thing, but let's try it. All right, opening an app. Paste. Crop. All right, let me pull this in as a source. Hang on. Are you guys seeing me in Microsoft Paint now? Yep. All right. So this one here wanted you to use arrow pushing to explain the following reactions here. So what I want you guys to help me out here. What is happening in the first step? So basically, what this problem is, it's giving you the reaction mechanism, but all the arrows are missing. I use Microsoft Paint a lot. I love this program. It's so simple and useful. It's just to the point. I am actually somewhat proficient at things like Photoshop and stuff, but yeah, this stuff is easy to use. So let's go ahead. Oh, we were doing orange arrows today, right? So let's use orange. So, I should make the line thicker. All right, you can see how that's showing up. You guys can see that. All right, what happens next? Oop. So the leaving group leaves like this. This is the RDS. Yeah. Kind of hard to draw with the mouse, I think. All right. Oh, hang on a second. We didn't actually cover this reaction yet. So at this point, if this were a substitution reaction, the nucleophile would attack one of these carbocations. But the question I have for you guys here is, what's happening in this next step here? Like, why does that plus charge move? What is that? What's going on here? This part right here. What's going on right here? Yep, that's a methyl shift. So I didn't actually explicitly talk about this during last time, but you should have come across this for sure in your studying. It turns out that after you have the formation of a carbocation in any mechanism, not just SN1, SN1 is just the first time you see it, but any time a carbocation forms, you have the possibility of a rearrangement. And that's because carbocations are relatively high energy, so they're the way that they can kind of shift just a little bit to stabilize that, they will. And that's typically done, sorry, he's like right here with the leaf blower. I'm not sure how well my mic's picking his leaf blower up, but he's right by the window. All right, I'm thinking keep going, hope for the best. Just lean a little closer. Claudio, stop! Okay. Okay, if you guys still hear. So, little side note is I feel like I'm a rich person because I have a lawn guy, but honestly, he does the job way faster than I would. And I'd be out there all day doing the stuff that he does like in 10 minutes. So he's a pro. He's like, done. So it's worth, and yeah, $100 a month. He comes every 2 weeks. Yeah, worth it. Yeah, support your local communities. Get a lawn guy if you don't have one. They're usually local workers. Anyway, what's happening here is that if you have the formation of a carbocation, if there is a possibility of rearrangement that'll make the carbocation more stable, it will occur. The main one that I want you guys to be aware of in this course is either a hydride shift or an alkyl shift. So a hydride shift is when a hydrogen moves, and alkyl shift is when a carbon group moves. So this is a methyl shift, so it's an alkyl shift, but specifically it's a methyl shift, because methyl is the group that moved. So yeah, so calling this an alkyl or methyl shift is okay. So let me show the arrow push. So essentially what's happening is if this methyl jumps over here, then this carbon becomes neutral, and then the plus charge is now over here. And the reason why that works, once again, let's write a different color here. Let's use blue. This is a secondary carbocation, and then this one is tertiary. All right, this reaction here is actually, the next part is actually next week. For this week, what I want you guys to be able to know is that a nucleophile can now attack here. But what we're going to see next week, let me just go ahead and draw it in. It's going to be on the exam anyway. Is instead of H2O acting as a nucleophile, it can act as a base and grab an H instead. Instead of going to the carbocation, like that, and then this has to break going that. Hey, getting pretty good at my arrow drawing on here. It's got to go slow, and then it'll come out okay. All right. Let's take a look at the next questions here. Switch back over to the browser. Oop. Did anybody do this one? This is a fun one. What happened here? My goodness. Yeah, this is all. I always do this problem, and no matter which OChem class I'm teaching, I always do this some point in the semester. It seems like whether it's OChem 1, OChem 2, 220, whatever. This is a fun problem, but I like to add to it. So let's go ahead and add a little bit to this problem. Yep, it's an intramolecular attack. Intramolecular happen a lot in chemistry, and most of the time when people are taking organic chemistry is because they're going into a field that's biology based, like, you know, medical lab science, nursing, whatever. And it turns out a lot of the intramolecular attacks happen in biological systems. Yep, we're gonna go over this one. I'm gonna modify the problem a little bit to make it a little bit more challenging, actually. So let's go ahead and do the same. I'm just one on paper, actually. All right. So that was a 5-carbon chain. So we had a Cl, 1, 2, 3, 4, 5, and then an OH. And the way I'm going to make the problem more challenging is I'm going to add groups on here now. So I'm going to go ahead and put a methyl over here, And then I'm going to put an ethyl over here, just to mix it up a little bit. Make it a little bit more challenging. Give you guys a reason to come to class. And then I'm going to draw out the NH2. The scene, that's okay. Yep, NH2. And then I'm going to go ahead and put the lone pairs on NH2. Like that, and that's a negative charge. Like that. So, what you might expect to happen here is that NH2 can act as a nucleophile or a base in this predicament here. So what I mean by that is we saw this week that NH2 could do a nucleophilic attack and attack that carbon, or it can do an acid-base reaction, which we saw the week prior, and it can attack the H instead. So the question is, which one is easier to happen? A nucleophilic attack or a deprotonation? Acid-base. Which is easier to happen? Based off of some of the graphs that we've seen in this class. Yeah, acid-base is much lower energy for them to occur, much lower activation energy. So if there's a choice, these strong nucleophiles that you often see with SN2, if there's an acidic H around, they're going to do an acid-base instead. So, boom, deprotonate, like that. And then 1, 2, 3, 4, 5. I'm just drawing a little bit smaller to give myself a little bit more room. That. Sometimes people will, honestly, if you left it like this here, like the other pieces of this that are missing are no longer going to be involved. But if you're worried about mass balance, what people can do here is this would likely say minus NH3. Deprotonation means removing a proton, removing an H. It's just the organic version of saying acid-base reaction. Deprotonation is a little bit smoother off the tongue. At least to the organic chemist. All right, so there, I'm just accounting for mass balance. And then you have your spectator sodium ion. And then, as you mentioned earlier, this can be an intramolecular attack. All right, so now we're on what I feel is the hard part of the problem, is drawing the next part. So we have to make sure that we get our correct number of carbons. So I like to number carbons on these problems, and then use the number of carbons to figure out how the ring is going to be, also to figure out where the groups are going to go. So I'm going to go ahead and number from this carbon here. You could have numbered from this side, doesn't really matter. So 1, 2, 3, 4, 5. So I have 5 carbons, and then oxygen is going to be part of the ring. So I have basically a cyclic ether. It's a 6-membered ring where one of the atoms is an oxygen. So I'm going to go ahead and just put it here. It's going to be like a hexagon shape, 6-membered, like that. Just for the sake of clarity, I like to highlight the new bond just so you can see exactly where the new bond is at. So let's go ahead and just say that that's the new bond that formed from the SN2 reaction. Hang on, I want to write a little comment here. You got to maybe get a chance to get caught up in the writing. So this was the intramolecular SN2. All right, so then we can go ahead and put our numbers back in. I have a feeling red's going to show up better here than the purple did. So it looks like I just got to pick a direction, really. It doesn't really matter. 1, 2, 3, 4, 5. And then carbon 1, CH2, carbon 2, CH2, carbon 3 has an ethyl. Carbon 4 has a methyl. Carbon 5 used to have a chlorine. We're done. Basically, this problem is the same as the one that's in the worksheet, just missing the branched groups. But I like to put branch groups on the tests and questions like this, so getting you guys ready. Any questions about this one? All right, so I'm gonna write another comment here about this here, so you can see for a situation where this actually comes up. Sometimes you can just ignore it so typically this only happens if a 5 or 6 membered ring forms. All right, so during your studies of stereoisomers, you may have come across conformational isomers. They're the ones that differ by bond rotations. I think it was in the actual handout, but I told you guys to skip that part. Just know kind of like conceptually what a conformer is. Please not right now, Tristan. Oh, he gave me a periodic table, so thank you, Tristan.
I put it on the camera.
I'm working. Please. Tristan. You are about this close to getting in trouble. Please go. Don't embarrass me on YouTube. The joy of parenting. All right. Anyway, so the short version, what I was going for here is that if you take Chem 241, there's actually a whole chapter dedicated to the stability of rings in organic chemistry, and it works out that nature prefers 5 or 6 membered rings. It's a stability issue. These types of rings tend to be more stable than rings that are smaller or bigger. So, yeah, it works out basically where if the ring is too small, like a 4-carbon or 3-carbon ring, they're too tight, and because they have the wrong bond angles because they're held too tight, and then the huge big rings are kind of floppy and they just fall apart. So these are the sweet spot for ring stability are 5 and 6 membered. 6 in particular is very stable. Yeah, if you actually look at a lot of your biological compounds that has rings in it, you'll see a lot of them are 5 or 6 membered, like pretty much all of them, just about. I don't think there's many exceptions to that. I was thinking of cholesterol in particular, which is a bunch of rings together. The structure for cholesterol. All right. So moving on here. Before I move on, were there any questions in here in particular you guys wanted me to work on? Like I'm probably going to do this page 6 and 7, but other than that, do you want me to do any other ones in particular besides 6 and 7? I'm for sure doing 6 and 7 during today's lecture. Any requests? 11. So yeah, there's a request for number 11. All right, let's do it. So here, consider the reaction equilibrium below and answer the following questions. It's asking you to draw the mechanism. Do not use the drawing above. Please redraw it. Okay, so let's go ahead and do this. Yep. I'm just going to go ahead and draw it on here. I'm going to make sure I include chirality here. I was showing chirality here on purpose for making sure that you accounted for that in your problem. It is SN2. It is SN2. And what I want you guys to tell me is, how did you know it was SN2? There's a couple tells here. So the tricky... I'm writing SN. SH. Add SN in my mind. All right, SH. So the first thing you want to look at, and trying to figure out which mechanism it is, you want to think about the structure of the substrate. What is the double arrow top demon? All right, so hang on, let me pull up the worksheet. So the question was about, like, what does this arrow mean? So typically, the equilibrium arrow is telling you the reaction is in equilibrium, meaning you have, notable amounts of both sides after the reaction has completed. Also remember the reactant does not actually stop. It's considered a dynamic equilibrium where it's constantly going back and forth, but the amounts are stable. So typically what we can do here, reaction arrows, there's a couple of different things you may see on a reaction arrow. They could be things like the reagent or conditions. Though there is no like hard rule on what goes in the arrow. It's just whatever someone wants to do. There's no rule. So once again, they are typically reagents or conditions. So DMSO is telling you the solvent, and the room temp is telling you the temperature. These are tells for what kind of reaction it's looking for, or what mechanism it was. So we have a secondary substrate, we have a fairly strong nucleophile, we have a polar aprotic solvent, and then room temp doesn't really make a difference here for this problem, but I'll write it anyway. Alright, I'm just copying the whole thing down, just finishing copying. And then plus CN minus. Alright. So back to presenter camera. Alright, so since I did redo it, I'm still following the rule. These are my notes, so I'm going to go ahead and use these for the mechanism. So here you want to show the backside attack of the SH. We decided SN2. Okay, so we have that attack, and then that leaves like so. So if you are being asked to show the SN2, it seems to be kind of standard to also show the transition state. But I want to make sure that you guys are understanding something. SN2 isn't the only reaction to have a transition state. Literally every single chemical reaction in the universe has a transition state. They are the in-between from A to B. So if you have a reaction with one step, it has one transition state. If you have a reaction with 3 steps, it has 3 transition states. Every step in your mechanism has a transition state. The only time you don't have it really a transition state going between them typically is like resonance, but I'm betting they probably technically do too. So, so once again, just to be clear, SN2 you typically show the transition state because the transition state explains the inversion of stereochemistry. But every reaction has the transition state. So I'm going to go ahead and draw that down here. So the center portion of the molecule is not doing anything. And I'm going to shorthand that as ET because that is an ethyl group. So typically what you want to show at the transition state is you want to show any bonds forming or bonds breaking. You also want to show any partial charges that are kind of facilitating the bond breaking and bond forming and all that jazz. So the way we show that is you want to use a dotted line. So I'm going to use red for my dotted line here. So we are going to see that the bond to CN is breaking. And I'm just going to make it a different color so it's really obvious what part of the molecule is actually reacting. And then we also have the incoming SH. And I like to write it as HS because this is showing connectivity. You don't want to write it as SH when it's pointing towards the left because it's bonded to sulfur, not hydrogen. Make sure you show the correct bond between carbon to sulfur in these drawings. It makes a difference. Believe me, it makes a big difference. All right, so next thing we need to do is we need to fill in our partial charges. So typically on partial charges, you only want to fill in the ones that are changing. So for example, I'm probably not going to bother filling in the partial charge on carbon because it's delta positive on both sides. So I think it's kind of pointless to show it. But what is changing is sulfur is becoming neutral, and then this carbon is becoming negative. So the in-between for both of them is delta minus. So delta minus, delta minus. To show that you have drawn a transition state to the reader, the way that this is conveyed is people will put a bracket around it, like that, and then the double dagger. That double dagger sign, remember, means transition state in chemistry speak. So if I were to have you guys draw a mechanism for an SN2, it's typically implied to draw the transition state, but I will specifically say draw the transition state. Or it means that. Yeah, it's a symbol from B. We were talking about that yesterday. All right, next question was, let me switch back to browser. Based on the mechanism you drew, what is the specific rate law for the reaction? So this is SN2, so it's going to basically be the rate times the concentration of the substrate and nucleophile. All right. Next one here is we're given the pKa of the conjugate acids of H2s, of cyanide and the HS anion. These are the conjugate acids. So remember, we're going to be doing a backwards kind of logic here. So I'm going to go ahead and write these in onto the paper here. So the SH was H2S was 7.0, and then HCN was 9.1. So switch back over to presenter. So all I did was I just wrote in the pKa's for the conjugate acids of these compounds. All right. So from these two, we can pick out which one is the stronger acid of the two. And if you're able to do that, you're able to pick out the stronger base of these two. So what do you guys think? Which is the stronger base? SH minus or CN minus? Stronger acid, weaker base. Weaker acid, stronger base. So you need to find the weaker acid out of the two acids. It's CN minus. Yep. So, do you guys remember which does nature prefer to kind of linger on the side that has the stronger base or the weaker base, do you think? We talked about this during the acid-base chapter. Just applying it here. Yep, it's correct. Strong acid, weak base. Weak acid, strong base. So once again, the question was, which side is favored? It's going to be the side that has the weaker base. I'd argue the reactant side is favored. This is a weaker acid than H2S. Yeah, it's so easy to get it twisted in your head, guys, but yeah, just kind of logically do it one little step at a time. It's really easy to pick the wrong side and thinking you got it right. So, and then we could also say that KEQ that was right. That was right. I don't know why I crossed that out. Alright, KQ less than 1, reactants favored. Alright. Next question was, assume the reaction is exothermic. I typically do that in all these problems. Draw the energy diagram plot. So, draw the energy diagram product of this reaction, show transition state, blah, 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 blah. All right. So we only have the one transition state, meaning, we only have the one step. So that means we only have one bump in our diagram. Reaction progress, you can also call it reaction coordinate. Typically how you see it in the textbooks, they call it reaction coordinate. And then it said assume exothermic, so that means the reactants are higher than products. So meaning it's going down in energy, it's giving off energy. So, and it's only one step, so there's your curve that you want to draw. And then we have our transition state would be there. And then this is delta G double dagger, also known as activation energy, E sub A. I thought I heard Zelda music there for a second. I was like, you playing Zelda? That's awesome. This part here is delta G of the reaction. Look at that. It's RXN there for reaction.
Daddy loves Zelda that.
Tristan,
Daddy
Tristan, you're done. Please just stop. You're done for today. Don't come in my video again, please. You're overstepping the bounds. All right. I want to mention this one right here real quick before we do the other one that I wanted to do. But before I move on, does anybody have any questions about this one? Before we move on? Really? So, I actually just finished Ocarina of Time like last week on my 3DS. Don't judge me. I'm a Zelda fan. I just love games in general, actually. But yeah, I recently just played Ocarina of Time on my 3DS. It's a great version of it. All right. So, no, probably my 30th time. I've beaten that game many times. I wasn't speedrunning it or anything, just kind of just playing through it for fun. All right. So let's go ahead and move on. So let's go ahead and switch over to the browser again. All right. So I want to take a look at number 9. This is kind of a trick question. What do you guys think is the right answer for number 9? Oh, a lot of people do that. That's not weird. Not weird at all. A is the correct answer. Awesome. Yeah, A is the correct answer here, everybody. So this is sort of a trick question here. So it's trying to get you to think that you're doing an SN, like a substitution reaction here, which it is. But it's putting a leaving group on the benzene. So the leaving group on the benzene actually cannot act as a substrate for SN1 or SN2. And the reason why is because it's on a benzene ring. This is not. We're going to go over benzene later on. Benzene does not react that way. This leaving group does not just leave on its own. If you put a carbocation here, it's very high energy. If you have it won't do a backside attack because this carbon is electron rich with the double bond there. So yes, does not undergo substitution at all via the way that we're showing it in this chapter. Benzenes do undergo substitutions, but they have their own pathway. They are electrophilic mechanisms, where these ones are nucleophilic. All right, so yeah, so basically this is your, this can actually be SN1 or SN2. And the reason why is because it's primary, but it's also a phenyl, which if you put a carbocation here, it's resonance stabilized. So it could be SN1 or SN2. So with that in mind, we can actually pick out which one it actually is off of this detail here. So what do you guys think? It's going to be SN1 or SN2 based off the conditions on the arrow. It tells you which one it is. So number 9 is SN1 or SN2. Yep, that is 100% correct. That is SN1. How did you know it was SN1? You did have a 50-50 chance to guess correctly, so how do you know that? Hang on. What's going on? No, so the question was, So anything attached to benzylic is non-reactive? No, if it's attached directly to benzene. Benzylic implies one carbon away. And so number 9 is a benzylic bromide. So let me clear. So this is a benzylic bromide. This is a phenyl bromide. The phenyl bromide is not reactive. The benzyl bromide is. Does that clarify that? Yeah. So you have two tails on the arrow for SN1. It's the fact that you have a weaker nucleophile, and you also have a polar protic solvent. This is a polar protic solvent here. All right. I want to go ahead and just do one more, and I think we're going to go ahead and call it a lecture, guys. Oh, and then I want to talk about the quiz a little bit. Where was that one I wanted to do? Where'd it go? There's one I wanted to do. There it is. This one. I want to do this one. So I actually gave this page was actually from one semester for 220, and I was banned from doing this kind of question on a test ever again. What was the complaint? Professor, you're only supposed to have A through E. And only one answer. Yeah, so it works out where there's actually 3 problems kind of buried into this one. So if you look at how the choices are broken up, what the choices are saying, this is literally 3 questions in one. So by saying it, choose all that apply. So first things first, you need to figure out what kind of mechanism this was for number 6. And you think, what is the so out of choices A, B, and C, what is the correct answer? In order to get that correct answer, you have to know which mechanism it is. So out of the first 3 choices, A, B, and C, which one applies? Yeah, so this is an SN1. Same reason why the last example we were doing was. It has a weaker nucleophile and a polar protic solvent. So C is the correct choice here. And then the next 2 sets of choices are asking about if you double the concentration of the nucleophile, also if you double the concentration of the substrate. So out of choices D and E, and then F and G, what is it? What is the combination of choices here? So yeah, SN1, that means that this one, is that right? Is D correct there? What do you guys think? Am I getting the wrong answer? Oh, no. Yeah, it's actually E and F are the correct answers here. E and F are the correct answers out of the next 2 sets of choices. So the concentration of your nucleophile does not affect this because it's SN1. And then the concentration of the substrate is affected by either SN1 or SN2. All right, so once again, the correct answer for this one was C, E, and F. C, E, F. Yeah, D was incorrect, guys. I was seeing if you guys would catch that was the wrong answer. All right, next one is the same kind of question. The thing here that it's telling you it's SN2, and there's differences in the compounds. They're slightly different. All right. So here we have basically A, B, and C. What do you guys think? Out of the choices A, B, and C, we're looking at number 7 now. Out of choices A, B, and C, which is the correct answer? Yeah, so it turns out technically X is like this much faster because there's less bulkiness, but I really don't want to split hairs like this in this class. So yeah, I actually graded this question differently depending on which class I'm in. I will accept A or C for a correct answer for this one. A or C would be acceptable for Chem 220. If you were in my 241, I would only accept A as the correct answer. All right, next two choices are asking about, yeah, so C for that. So the next two choices here are asking about the chirality of the product after these substrates react. So will they both be optically active, or just one of them will be optically active? What do you guys think? After these undergo SN2. Yep, it turns out that if you start with an achiral compound like this, your product is still achiral. All right, next one here is, I'll quickly do these here. So next one here, the concentration of the nucleophile will affect the reaction rate. This is SN2, so will affect it. This one, wait, F. All right, and then if we're saying this is SN2, then these prefer polar aprotic solvents like DMSO, dimethyl sulfoxide. This is DMSO that was used in an earlier problem. Interesting thing, I really like mentioning this to this particular set of students. Yeah, so X is chiral because of the double bond. The double bond makes it chiral. All right. So DMSO is a common solvent used for many different biological-based procedures. And the reason why is apparently that solvent is very lipophilic. Do you guys know what it means if I'm saying that DMSO is lipophilic? What does that mean? You guys have done some lab stuff and some biology. What does lipophilic mean? It likes fat, yes. Lipo is fat. It interacts with lipids. So what ends up happening is if you ever work at DMSO in the lab, I recommend literally double gloving with it. So when I used to work at DMSO, I used to put a pair of nitrile on my hands, and then latex over the nitrile. And the reason why, because I wanted not even a drop to touch my skin. And I also wore a lab coat too. The main reason why I didn't want any DMSO to touch my skin is because it's very strongly lipophilic, and then if you have something in there like cyanide, you're doing an organic reaction and you get a drop on your skin, it'll absorb right into your bloodstream, carrying along whatever reagent you had in the solution. So you can instantly deliver these really strong chemicals to your bloodstream. Very, very bad. So yes, if you guys ever work at DMSO, take very strong precaution. It is dangerous. And it's not because of DMSO itself, it's because of the fact that it carries anything in it along for the ride instantly into your blood. So yeah, instantly, it's almost like an injection, how fast it is. From what I understand, that's what I've read. So I take extreme precaution. All right, I'm gonna do one last problem here, but I'm gonna kind of leave you with the question. Maybe try the mechanism basically. So let's go ahead and take a look at this one. Oop, with number 8. Yep. So there's number 8. So this is gonna be a similar to the one we did earlier with the intramolecular. And I'm actually just going to draw drawing out the compound right now. Like this, and then NaSH. DMF is dimethylformamide. That is an SN2 solvent. It's a polar aprotic solvent. Typically the ones that are protic, remember, they have acidic H's. They're most commonly going to be water or an alcohol of some sort, like ethanol, methanol are the common ones. It's never used as an alternative because DMSO does have toxicity problems on its own. That's never going to be a thing in the hospital. That would be super cool though, but as an option, but no. I was thinking for like children, if we had a solvent that was safe to use to deliver medicine to children, and you didn't, or sorry, some adults are afraid of needles too. But yeah, for those that are afraid of injections, it'd be a nice alternative to be able to just rub it on their skin and then call it good. But nope, not yet. We haven't figured anything out for that yet. So 1, 2, 3, 4, 5. This is gonna have a similar product as the other one. I'm drawing the answer now. Let me just switch over. So I'm just drawing the answer to this one, and I'll let you guys figure it out. So that is the product for this question. That's what I was specifically looking for, was that. This is number 8. Yeah, don't forget your Lysol and ultraviolet light injections this week, guy. So ridiculous. All right. So I'm a little behind on writing your quiz. I normally would have spent this morning getting your quiz ready before class, but I really want to get your exam done. I still had like half the class left to do on the exam grading. I was planning on working on that probably tomorrow morning. So honestly, guys, after class, I'm usually just dad after class. So that's usually why I don't do a ton in the afternoon, is because I usually end up just becoming dad and doing family man stuff. So just because my wife is actually working right now upstairs for Netflix. Are there any questions about anything? But anyway, what I was thinking about doing, because I'm gonna be a little bit late in posting the quiz, I'll push back the due date till Sunday this week. So yes, there is gonna be a quiz this week. Every week we have something due this week. Yes, every week there's something due. Quiz or exam every week. So I do not get free Netflix. So my wife works for a company. I'm actually gonna post a link in the chat here, because her job is always hiring. Hang on, let me do it right now. If anybody's looking for at-home work, these guys are hiring, and they're in town here. So basically, they're called Sutherland Global. They are basically a call center for hire. So other like large companies, like Fortune 500 companies, will contact them and basically hire them to run their call center. But yes, so this kind of work is not cut out for everybody, which is why they have a high turnover. So you got to remember, if you're working at a place like Netflix and you're working for customer support, people are not calling you because they're happy with their service. They're calling you because they are mean, or being mad is why they call it typically. Yeah, so customer service. So keep in mind that there's a reason why they have high turnover. Another thing also, since they moved to working at home, you have to have all your own equipment. So you have to have basically your own computer and mic and all that kind of stuff at home. I would hope that as a college student that most of you have that already. So I hear a lot of stories about. So my wife is a manager, and so when you call there and say, "Let me talk to your supervisor," they might put my wife on the phone, and she hears a lot. I hear a lot of stories about stuff that people call in for. It's ridiculous. Like people calling in because their TV's broken, and somehow Netflix's fault that her TV's broken. You know, that kind of thing. Yeah. Oh, so yes, it looks like someone in the here already worked for a call center. It's all complaints. Yeah, it's all complaints. So, all right, guys. You have any questions about anything? So just make sure everybody's clear. We have that. Hang on, let me go to the class stuff here. I keep forgetting to talk about something here with the class. So I'm pulling up the worksheet submission assignment right now for this week. I didn't put any content in it yet, but hang on. I have it in Planner, what I wanted this week. I just want to make sure there wasn't a mistake in here. Yeah, we're not going to be able to do E1 and E2, guys. That's going to have to be until next week. So, well, I'm not going to have a chance to lecture on it. So do not worry about the worksheet for the elimination. That's the next worksheet. Like, that's the 2.3, I believe it was. So I'm only going to be collecting the 2.2 worksheet this week. But we do have a quiz. So I'll just go ahead and push the eliminations back next week, and we'll just do all the alkene stuff next week. Because I think we're supposed to do additions next week, if I remember right. Let me double check. So, got the insight. I'm getting the view that you guys don't get to see. This is all the stuff that I have hidden from you guys right now. I think week 5 with addition reactions. Yeah. Yeah, we'll go ahead and do eliminations briefly, guys. So definitely make sure that you study over the elimination reactions. Oop, I put the wrong thing up there. Yep, this is what I was looking at. I keep getting sidetracked. All right, so yeah, once again, the one worksheet is due. I'll have a quiz up, and then I'm gonna go ahead and push the due date back because I won't have this quiz up until tomorrow. So I'm getting it up a day late, but I'll give you an extra day to work on it. Sound good? Is that fair enough? I figured if I give you guys an extra day because I'm a day late, I would have no complaints. All right, so I want to talk about one last thing before I cut the stream. I'm not sure if you guys heard about the mask, what the governor passed or talked about. Sisolak wearing a mask. I really felt that people should have just been policing themselves, but apparently it's mandatory now. So if you guys want to go into any kind of public establishment, you need to be wearing a mask. Yes, masks are mandatory now. They should have been from the get-go. I don't know, my personal belief on this whole mask thing, that people have their rights to do whatever they want, but I feel like you're being a moron and disrespectful to your fellow citizen by not wearing a mask. Because how many people are asymptomatic? You have people saying that, oh, I'm not sick, so I don't need a mask. Yeah, you might be asymptomatic and giving it to like 100 other people that may be symptomatic. It's ignorant. Please wear a mask, everybody. It is ignorant not to do so. It is disrespectful to your fellow citizens. Not yet. Not yet. So I'm not sure if you guys actually watched the actual presentation or the talk that he gave. I watched it yesterday, and and he basically said in much nicer words, "Don't make me make this a law. I don't want to arrest people. Don't make me make it a law, but we will if we have to." So right now, from what I gathered, is businesses are going to have to enforce it for now, and then if the businesses don't enforce it, he's holding them accountable. So basically, if the police pop into a business and customers are not wearing masks, the business gets in trouble, not the customers, and that's yet. So I'm really worried this is going to turn into a mess out there. So when you guys go, I'm worried about people being like all aggressive and mean and fighting each other at the doorways of the grocery stores now because they can't go in because they're being stupid and not wearing a mask. Yeah, exactly. No shoes, no shirt, no mask, no service. 100% agree with this. I know I'm being kind of mean right now, but if we would have did this from the get-go, I think Corona would have been gone by now. All right, guys, I'm going to go ahead and cut the stream. As usual, I hang out in the Discord and answer questions. So be safe and sane, everybody. Wear your mask. It's kind of mandatory as of tomorrow anyway. Have a good one, everybody.